Alright guys, welcome to Random Variables, Distribution Models, and lots more. So, first off, in order to make probability more mathematical, a random variable is associated with a random event, which means it is locally and immediately unpredictable. And in order to make it clear what the event space is, we define a variable x to be our random variable. Now, the x could actually be associated with heads or tails, car is red or blue. But what we like to do is we usually like to make x an element of a set that lives inside of usually the integers, maybe the natural numbers, sometimes the complex numbers, or even just the reals. So it can be pretty crazy. So here's a pretty simple random variable. X is associated with 0 or 1. And let's make 0 be associated with losing, and 1 be associated with winning. Now, it might be you're shaking a die, and the shaking of that die, losing happens if you shake, let's say, 3, 4, 5, or 6, but winning is associated with 1 or 2. Well, then we can associate to a probability of x the following: that the probability of 0 is going to be the probability of losing, which is 4/6, and the probability of 1, which will be 2/6. Now, that's a random variable. You might not call it fair, but we don't really care. We simply say those are the probabilities. Now, I can mess with this, and I can just say 2 rerolls. What would that do to this? Well, this would be wrong. The probability that you win, well, is 1 out of 5 possible outcomes. And the probability that you lose is associated with 4 of 5 outcomes. And you get a 2, you just reroll, 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 reroll. And it turns out this is a perfectly good probability where the 2 is like, didn't count, do it again, didn't count, do it again, didn't count, do it again. I remember as a kid when we were shaking dice, if one of the dice landed on an edge and was crooked, oh no, 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 doesn't count. So probabilities don't have to be exactly what you expect them to be. A lot of probabilities are empirical based, other probabilities are theoretically based. So what are we going to do with random variables? Well, the random variables allow us to construct models and descriptions of things, and it allows us to say what probabilities really should look like. So first off, there are 2 types of random variables right off the bat. There are discrete, and that's this one. It takes on just a finite list of numbers. And then there are continuous, and those are random variables that take on lots of things. So imagine throwing a dart at the real line, and basically it's a big blackboard, but it's a line. The dart hits the blackboard, and we just draw a line down, and x is your random variable. And let's say the dartboard is from -5 over to 4. Well, then x is in the interval from, well, I don't know, can we hit the edge of the board? Let's put it -5 up to 4. And so the random variable takes on values between -5 and 5. How the probabilities will be defined, well, we'll get there. We're going to start with the discrete cases, usually the easiest. So first off, we make a set that collects together of all the values of x, even if x is described by winning, losing. So x is that element of a set S, which is associated with events that we've described. First and foremost, when we work with a probability function f, then this must be greater or equal to 0. Now, if we restrict it to not be 0, then we're talking about a restricted set S, which is a very nice thing to do. Why should we write down X is an element of the set S, which equals 0, 1, 2, 3, 4, and the associated probability of 0 is a quarter, associated probability of 1 is a quarter, the associated probability of 2 is a quarter, the associated probability of 3 is a quarter, and the associated probability of 4 is 0. I mean, anything but 0, 1, 2, and 3 must be 0. Why list them? So most people, especially in the discrete case, say, oh, sorry, not equal to 0. Just makes things a lot nicer. We often will extend discrete functions to large spaces, and everything that's not in the normal set S will be referred to as 0 values. Frequently, and without fail, I'll refer to the set S as the support of the random variable X. Now, if we also have that the sum of all the f of x's, x and s, add up to 1, and when you take a collection inside of a set A, probability of a set A living inside of S, then it is the sum over x and A of the f of x's. Well, that looks like how we defined a probability function in the first place. However, since it's discrete, we've been using f, and we actually refer to f as a PMF, probability mass function. Now, many of these probability functions we can construct are models of reality. They may not be right, they're just models. So consider this one. F of x equals 1/6. X is an element of S, which is equal to 1, 2, 3, 5, 6. This is an example of what we call a fair die. Every number is equally valued. This distribution is a unique distribution. It's referred to as the uniform distribution. But it is a uniform distribution, a bazillions of them. You could take f of x equals 1 over n, and x is an element of s, which is equal to a start value, a start plus an increment, move all the way up to an end value, and make sure that the size of s equals n, and this is a uniform distribution, not uniformly over some set of numbers, but a consistent set of numbers, and it's a fair value. So there's lots of ways to have a uniform distribution. The standard way is that the increment should always be +1. It's not necessarily the fact that you have to go by anything else. That's the most common uniform. But they're all actually allowed, but the book refers to that as the uniform. Now, we draw PMFs as charts that look like this. Suppose this is 1, 2, 3, 4, 5, 6. The heights are the f of x's, and you've got to make sure the sums add up. Obviously, this is not a fair in the sense of mathematicians, and humans saying, oh, this is a fair occurrence. Well, lots of things are fair, but not actually uniformly distributed. Now, as I promised before, the hypergeometric distribution is actually an easy distribution, and we're going to write it down. It's one of my favorite distributions to test students on because it looks complicated. It's not. So first I'm going to write down the distribution, and I'm going to have you note right off the bat, there's a lot of variables in here. Since I'm using capital N1, that means it's a fixed number and you should know it. X is going to be something in the domain of the function, which means the support of the probability mass function. Then there's going to be another constant, N2. And now we're going to do another number, little n, which it's not a capital, so it seems like it's a variable, but that shouldn't be written that way. I'll fix it in just a second. We don't like this, but you'll see how we fix it. Minus x divided by nx. So before I go on here, I'd like to walk through the analytical part in your brain of what this means, the meaning. I mean, we should be able to figure it out. So first off, this reads n choose n. So I want you to think of 52 choose 5. Why, that's the number of hands dealt without order, without replacement from a standard deck. And how big is the hand? Hand size equals 5. Deck size equals 52. So it seems like this number n here is really something that's fixed when you start the problem. I'm not a big fan of using little n there, but it's the most common thing. Now, because little n can be changed, it is kept small, but there's something else going on here. Up here, you're looking at something and you're picking x of them. So if you remember, we tried to count how many ways can you get 3 kings? Well, if there's 4 kings in the deck and you want to choose 3 of them, then you can see that x ranges over 0, 1, 2, 3, 4. But then the remaining cards are the deck 52 minus the 4 kings. So an example that we've done already is 4 choose x, 48 5 minus x over 52 choose 5. This was a very reasonable f of x. It was associated the probability of getting x kings. Now clearly when it's written this way, x could be anything from 0, 1, 2, 3, 4. In fact, this number says it can't be bigger than 4, and it can't be less than 0. This says it can't be bigger than, 5 minus x? Why is that? Because you have 5 cards in the deal, so if you had none of the x's, this could be up to 5. It's not associated with this. That number was the size of the hand, as was that one. Now, when we have lots of numbers like this, a more consistent and normal structure is to do the following. X is the random variable. We will make use of n, which is equal to n1 plus n2. We will make use of n. And here is a more common way that this should and could be written. And that removes some unclarity, let's say. And it makes it really clear some relationships and things that are going on. Did you see here that it was n1 plus n2? No. So, let's formalize the hypergeometric distribution. So, n objects. So, finite. n1 objects alike or equal or indistinguishable. That's the fancy math. n1 objects indistinguishable, but they're n1 different things. It's like saying 8 black marbles. Even though they might be bigger and smaller, we refer to them as indistinguishable. Then n2 is by definition n minus n1. It could be yellow, green, black, yellow, green, blue, lots of different colors, but we're only focusing on one object. This is characteristic 1, and the rest are not characteristic 1. That makes the hypergeometric very interesting. There can be many types of objects, but we focus on just one of them. Hence, 52 cards focusing on the kings. There are 4 kings, and there are 48 not kings. And that's how it comes into being. A mathematician makes deep choices sometimes on how to make this work. Now, we then also, n is the selective number from a group of these n objects without replacement, and x counts the number of characteristic 1 objects collected. Well, that clearly makes x bounded by n1 and up to 0, so x is from the support of 0, 1, 2, up to n1. There we go. Now, what makes the hypergeometric interesting is it is asymmetric. Usually, it is possible to be symmetric. And what's really interesting about it is when you get capital N bigger and bigger and bigger and bigger, what happens is it starts looking like a very common curve that you've seen before called a normal curve. That's really neat. It's nice to know that some of the things that we've talked about before, Gaussian and stuff in different places, that we now have associated with it an object that looks like this, the hypergeometric model. And the formula of x with n equal to n1 plus n2 with a choice of n is choose x of the n1s, choose n minus x of the n2s over n, choose x. It's like counting those cards that we did before. All right, hypergeometric. Well, you should be able to calculate some of these and draw a nice picture. Calculate, picture, questions. That's interesting. So for example, let's suppose you did a model and it looks something like that. You calculate it, you drew a picture, you have some support. Now you might ask a question, well, why is it big in the middle and slopes off? Or let's suppose you got one that looked like this. This could be really interesting. A void in your model. Strange. When we calculate, it's learning how to look at things, assign a random variable, determine a probability, draw a picture. But when we finally get the chart, and we refer to them as bar charts, what is the right name for these things, these histograms, especially when we don't have exactly some of the best things in the world? Well, they get kind of dicey. Now, we're asking these questions is what we're going to do with our models a lot. So suppose somebody teases you and say, oh, I've got a model. It's a kx. K is a fixed constant. K from the reals. Oh. We'll draw a picture of this. Well, that's really hard. There's not enough information. I need to know what the domain, the support of my function is so I can actually draw it. So, suppose I tell you that x is from a set that is at 10, 11, 12, and goes up to 100. Well, let's write this out. So, f of x is kx, and k is a real number, and k times anything from 10 will be positive if and only if k is at least a positive number, right? But we still don't know it. How about the fact that if we add up all of these guys, we've got to get 1. Well, what will we do? Well, I think this says you pull out the k, and then you add up the x's and s. But can somebody tell me what x from 10 to 100 adds up to? Do you remember? I think that comes from something that some of you should remember from calculus. So here's where I'm going to stop, and I'm going to ask you, look up or remember the following formulas. What is the sum of r to the I equals some constant 1 to constant 2? Can you do that one? What is the sum from I equals some constant to another constant of just I? Or, what is the sum from I equals some constant to another constant I squared? I bet you know these three. By the way, one of these is a very famous name because an approximately 7 to 8-year-old boy figured it out in Germany one day, and in school. And this one is Dr. Sorensen's favorite series. You should know its name. All right, there we go. I believe there was a mistake in that list that said that the first homework in this chapter was burn bile, but this is really the random variable histogram graphing one. The next section will be mathematical expectation. All right.